I want to talk about local properties of modules, so stock local properties. Of modules. Okay, and they can either be about modules or morphisms of modules. And let me explain what I mean. Okay, so a property P. So definition. Okay, so like let me just say kind of the idea first, right? So what's going to happen is that so localizing we found out is a very nice functor. Okay. Well, one thing that you can do, right, is you can check that if you localize at every maximal ideal or equivalently every prime ideal of a module, if you localize it and you find that it's 0, that's going to tell you that the module is 0. So there's kind of an equivalence between the module being 0 and the module locally being 0, stock locally being 0. So the same thing, you can do the same thing with injectivity and surjectivity. So a morphism will be surjective if and only if after every localization at a prime ideal, it'll be, did I say surjective? And the same thing goes with injectivity. Same thing goes with flatness, right? Flatness is something that you can check locally. Same thing goes with this property being called integrally closed or normality, right? And so there's just kind of this zoo of properties that you can check stock locally. And it's very nice because over local rings, these properties become very easy, right? So essentially, we'll find out that over a local ring, well, you need to have some finite conditions on your module, but free, projective, and flat are the same. Okay, so going local is super nice. Okay. And there's a bunch of exercises on it. That being said, I'm just going to kind of formally get into what the definition is. So definition. So a property. Okay, now I'm going to do a fancy P. Fancy P of, is that a good fancy P? I don't know. Do I really want to stick it? Let's do fancy P like that. A property P of an R module M is called stock local, right? If and only if, well, let's say if, so P or that's my fancy P, P holds for M if and only if for every prime ideal, P holds for M localized at P. Okay, so then there's kind of this other version, so definition, a property P of a morphism of R modules, F from, let's say, M to N, is stock local. If and only if P holds for F, if and only if, so for all P in spec R, P holds for the localization. Okay, and let me just say that, so what are the quantifiers here? So this is, so P holds for, yeah, I guess it's stock local. Yeah, I guess this is fine. I was worried about the quantifiers, but it's just a thing that you do about all morphisms, right? So P holds for a morphism if and only if it holds for all the localizations. Okay, let's make it better P here. Okay, all right. So like the examples that I gave, what? Right. So m is equal to 0. Okay, so this is a property. So okay, f from m to n being injective or surjective. Okay, those are Stalk local, and m being flat. Okay, and then there was a property of rings that I said, which was being normal as a ring. That's not necessarily, it's not a property of modules. Okay, so all right, so let's do the first. Let's give a theorem. Let me see. What else did I want? I needed to remind you guys of something. So just kind of like a reminder before we get into this. I'm going to be using this fact, right? So that localization. So if let's say m, or let's say localization at any multiplicatively closed set. Set is an exact functor. So it takes injections to injections and surjections to surjections. Okay. So that means that if I have an exact sequence of modules, R modules, and I localize at some S, some multiplicatively closed subset S, then that exact sequence maps to an exact, it functorially induces another exact sequence. Okay. Okay. So okay. So now let me do the dilemma that I wanted to prove. Maybe I can call this a theorem. Okay, so let M be an A module. Okay, so where A is a ring. Okay, so the following are equivalent. Okay, so 1 is that M is 0. 2 is that MP is equal to 0 for all P prime ideals P. The third thing that we have is that MP is equal to 0 for all, let's say, P so for all maximal ideals. So you can check this property either at maximal ideals or at all the prime ideals, and that'll be equivalent. Okay, so let me give you the proof of this statement. Is it clear what this statement means? We get thumbs up or something.
Yep.
Okay, cool. Proof. Okay, so I claim that 1 implies 2 implies 3. So this is clear because localization. Well, I mean, well, actually, the 0 module has to go to the 0 module under localization, right? So to map to 0 under localization. And So every prime ideal can be further localized into a maximal ideal. Okay, so that has to do with the property of what property does it have to? So that has to do with the way that localizations kind of commute with each other. So the localization of a localization is just a localization. Okay, and so to do that, you use the universal property. All right. So all right. So now let's do the hard direction. So let's prove that 3 implies 1. But you'll see it's not so hard, actually. I mean, it's a creative idea, right?
What? I'm not sure I caught why. Why is 2 to 3 obvious?
So 2 to 3 is obvious because so if you localize at a prime ideal, right, it's either maximal itself or it's not maximal. And then after a further localization, right, it'll be sorry. Why does 2 imply? Okay, so actually 2 implies 3 is really actually every maximal ideal is prime. That's maybe the easiest way to do it.
Okay.
Right.
Yeah.
Let me write that. Okay, so that's much better. So 2 implies 3. So here, let me just write that here. All right. I guess I don't know what I was talking about. So yeah, this is the way to do it. Yeah. Okay. All right. So let's do 3 implies 1. All right. So what we're going to do is we're going to suppose that the localization is 0 at every maximal ideal. So suppose MP is equal to 0 for all P a maximal ideal. Okay. And then we're going to suppose, for the sake of contradiction, that M is not equal to 0. So suppose, for the sake of contradiction, M is not equal to 0. Okay. So then there exists some non-zero element, right? X and M, non-zero, and okay, so we're just going to take that, and what we're going to do is we're going to look at its annihilator. So let's do this. Sorry. Okay, and so we're going to have that that 1 is not an element of the annihilator, right? Since it's not 0. Okay, so this is a proper ideal. I mean, so this is not this is an ideal. So it's not equal to the unit ideal, right? And so this means there exists a maximal ideal, some maximal ideal, M containing I. Okay, so now we know that X is non-zero, but after we localize, it will be 0. Okay, so we have this thing here. This is 0. Okay, so I'm going to use this a little bit later. Right, I'm going to use the relationship between the annihilator and this maximal ideal. Okay, so we know that this is 0, and so this means that X over 1 is equal to 0. Okay, and so this means that this is true if and only if there exists some S in SM, the thing that we localize at. Let me just remind you that this is A with M removed, such that S x is equal to 0. Okay, so that's what it means to be 0 after localizing. Okay, so this means that, right, so this is the same thing as saying that S is an element of I, this annihilator ideal. Okay, but what do we have? So, but this is an issue, right? So the issue is that, so we have to write this down. So I claim that this is a contradiction, okay? So, but you know, this thing here, so I is contained in M, right? And this means that, right, that so A set minus M is contained in A after I remove the annihilator, right? All right, so in particular, there can't be an element in A set minus M that annihilates it. This gives a contradiction. So, you know, this means that SM intersect I is empty. So we have a contradiction. And hence, M is 0. Okay, so there can't be a non-zero element. This gives the contradiction.
Could you give an example where it's difficult to tell that a module is 0?
Yeah. So there's like open problems. So like even to telling when certain abelian groups are 0 is hard, right? So like but these are like finite groups. You want like some interesting one.
Would they be like associated to a knot? If it's the unknot or not?
Yeah, so that's like a fundamental group thing, I think. So I think you take the knot complement and you take the fundamental group of that or something. So like you could take, so there's things like Picard modules, or you could take like an ideal class group. That's the finite group still. But like, so let's see. I mean, that's another group. Let me think of a good module. So like the vanishing set of something, like there's you know you can take an element and try to see if it vanishes anywhere. I don't know. I don't have a specific one off the top of my head.
Yeah, I was just wondering when it would be more useful to check zeroness locally as opposed to being able to tell if a module is 0.
So I mean, this is like more a theoretical, right, tool. So like to develop a big theory. So like to do things to define things on schemes, right? We'll do everything like Stalk locally. This is one of the things that we'll do. So yeah. So I think we'll see lots of examples of this sort of thing in next semester, right? If you're going to take my curves and surfaces class, there'll be tons of examples of where we want to check stuff. I mean, there's going to be lots of interesting modules there. Okay. Other questions on this? That's a good question. Okay. All right. So now let me. So now we have that. So a module is 0 if and only if it's 0 locally, Stalk locally. Okay. So we proved that being 0 is a Stalk local property. Okay. Okay. So now let's prove. So we proved. Let me just. I guess I should write that down. Being 0 is Stalk local. Okay, so now let me do another lemma or theorem. I guess we'll call these theorems today. Okay, so let phi from V to W be a morphism of A modules. Okay, so the following are equivalent. One, so phi is injective. Two, phi p. All right. Okay. Okay, so phi p is injective for all p in spec A. And three is that phi p is injective for all p in max A. Okay, and so let me just say that we can do the exact same thing for search activity. All right, so so let me just do the same thing holds for phi surjective. Okay, I'll do that one later. Out of laziness, I just don't want to write everything again. Okay, so all right, so we're gonna check that being injective is a stock local property. I don't know why I made this phi different. Okay, so let's do the proof. So I guess I need a reminder. I already told you. I told you that localization is an exact functor. Okay, so it takes injections to surjections, or injections to injections and surjections to surjections. So when I take a stock, so taking a stock is localizing at a prime ideal. So when I take stocks, that's exact. So, okay, so proof. Okay, so one implies two implies three, because since localization is an exact functor, and what was I saying? And so since localization is an exact functor, and all maximal ideals are prime. That's the two implies three part. Okay. So all right, so we have that. Okay, so now we'll do the hard part. Let's do three implies one. So we're going to assume that the map is injective here for all p, and then we're going to show that phi is injective, the original one. Okay, so what we're going to do is we're going to let v prime be the kernel of phi. And I'm going to show that that's 0. So now you can already see that I'm like going to localize. Okay, so the sequence here, 0 to v prime to v to w is exact. Okay, so since exactness is a local property, right? So this implies that this thing here, 0 v prime of m to v of m to w of m to 0 is exact for all maximal ideals. Cool. Okay, so since phi is so by hypothesis, v prime of m is equal to 0. So and this is the map phi of m, since phi of m is injective. Okay, so the kernel of the localization is the localization of the kernel. All right, and this holds for this holds for all M, all maximal ideals. This holds. All maximal ideals. Okay, so this implies that, so by the previous lemma, or previous theorem, we're going to have that v prime is 0. Okay, and that's the same thing as, this is the same thing as this map being, so we have this is a kernel. If the kernel is 0, then the map is injective. Okay, so this means this is the kernel of so the kernel being 0 is equivalent to being injective. All right, so that proves this part, 3 implies 1. Does that make sense? Okay, so what am I going to do the, so let's do the red one, right? Okay, so what was the strategy? So the strategy is I'm going to reduce it to the case where I'm going to test if a module is 0 by looking at the kernel, and then using that localization is an exact functor. What should I do to show that something is surjective?
Look for the case where the image is 0.
Yeah, the co-kernel. You're going to take the co-kernel. So the co-kernel is mod the image, right? So instead of using the kernel, we use the co-kernel. Okay, so 3 implies 1, and so I'll just do 3 implies 1 in the surjective case, but the other properties are just as easy because of exactness. Okay, so this is the surjective. Okay. Okay. So yeah, so what we're going to do is we're going to define. So what we're going to do is we're going to let v prime prime or maybe we call w prime prime. W prime prime be the co-kernel of phi. And what's the co-kernel? So the co-kernel is the quotient, right? It's going to be v w modulo phi of v. Okay, so we have an exact sequence. There we go. So we have an exact sequence. So we had v to w, right? V to w. Oh, you know what? So I didn't really have this part of the sequence here. Sorry. So we only had that it was injective. We didn't have that this map was surjective. So I shouldn't have written that other part, that other end. Okay. And in this part, I'm not going to write the first, I'm only going to write this thing. W prime prime. Okay, so we have that we have this exact sequence. Because the image of this is the kernel of the next. So I guess the kernel of this map is the image of this one. So that's saying that this map is surjective. Okay, so we have this exact sequence, and so so by hypothesis, or actually, so not by hypothesis, but let's just say, so we have this exact sequence. And now we localize the exact sequence. So this is by properties of localization. So for every maximal ideal, we localize. So we have V here, W here, W prime prime here, and this is 0 still. Okay, so this thing is exact. Since localization is an exact functor. Okay, and then this is the map phi M. Okay, so the stock of the map phi. Okay, now by hypothesis, this is surjective. So by hypothesis, we suppose that every stock on every stock that it was surjective. Okay, this is equivalent to this thing here, W prime prime localized at M being 0. All right. So W prime prime at M being 0. Okay, so this is true for every maximal ideal, right? And so since for all maximal ideals, so we have that W prime prime. Okay, so that's applying this is applying the previous theorem about being 0. Okay, and so W prime prime being 0, right? So this is true if and only if the co-kernel of this map is 0, if and only if phi is surjective. All right. All right. So does that make sense? Kind of the strategy.
Where do we use the maximality of the ideals we're localizing at?
In the hypothesis. So
I mean, as opposed to using them being
this
prime.
at a prime ideal as well.
Okay, that was the question.
I mean, but this is a weaker condition, so this is a stronger statement. So it's not that you have to check at every prime ideal. It's enough to check at maximal ideals.
Got it. Thanks.
Right. So it's like better. Yeah. I mean, yeah. So I guess we're plugging it into this. So yeah, that's a good question. Is like, how can you modify? If we go back to this one here, right? I mean, you could say at every localization, but you could fiddle with this. You know, these conditions here. It's true that M is 0 if and only if it's true at every localization. And then I guess we did use the maximality hypothesis. Like it comes into this part of the proof where every ideal is contained in a maximal ideal, right? And so it's hard to get away from that here in this proof. Okay. All right, so let's do. I want to do flatness as a local property.